So instead of summing from the first term to the last, if I change to that relationship, I sum from the last to the first, but the result of the summation doesn't change. Okay, perfect. Now, what we learned so far? We learned that there is a category called the linear models that allows us to compute the river discharge as a linear function of rainfall. We learned that this approximation of linear function is useful, but on the other end is not really justified from a physical point of view. But it's justified if we consider that it's very useful. Especially in the past, it was very useful because linear computation was much easier than nonlinear computation. Now, with the computing power that we have available, the difference became less significant, less important. But in the past, it was very important, very useful to have the opportunity to apply linear models. So we learned that we have this category of models. We learned that this category of models can be written in compact form by using this relationship, where the instantaneous unit hydrograph plays a relevant role. And we learned that for the case of the linear reservoir, we learned much more. We learned how the model is conceptualized, how it is integrated, how H, what is the form that H takes, the mathematical form, and also we learned the behavior of the model for constant rainfall in the long term. Perfect. Also, there is to say that we started to develop an exercise where we will apply this model. And this exercise will be continued on Thursday for 3 hours. And Emanuele will teach instead of me. I have a department council on Thursday, cannot teach. I will teach on Friday. And Friday is again theory. On Thursday, please bring your PC and you will work on the PC. Now, there is still one issue pending, which is the estimation of K. And K is a parameter. And basically, the estimation of K is reconduced to the general problem of estimating the parameters of a model. So how can a parameter of a model be estimated? Now, let me anticipate a little bit what we will do later. In the next lectures, I want to introduce to you a more complicated, more detailed rainfall and runoff model. And this is very useful because these linear models, they are indeed, in some cases, they are useful. And the reason for their usefulness, as I said, is that they are linear. And they were much used in the past because of the easy mathematical tractability. But now, with the increasing availability of computing powers, we also developed, hydrologists developed more complex model, more detailed model. I want to give you an example. So basically, before closing this topic, rainfall runoff modeling, I want to explain to you another model, which is a bit more complicated. And the model that I will introduce to you counts a larger number of parameters. In this case, we have only one parameter, which is K, and it is quite understandable that if the model becomes more detailed, the number of parameters increase. And in fact, I will introduce to you this model that counts 5 parameters. And in the sequence of my lectures, as you can see them on the website, there is rainfall runoff modeling first and parameter estimation later. I prefer now to anticipate parameter estimation now, because in this case I think it's easier to understand how parameter estimation works because we have only one parameter. So I prefer to anticipate parameter estimation before introducing the more detailed model. So basically, I would like now to turn, because after these slides, this is already a slide The next one is introducing these more detailed models. I prefer, if you allow me, to postpone this, and then I pass to the next lecture. Okay, the next lecture, which would be what you can download. Not sure. No, I don't have the connection, unfortunately, and therefore I cannot. Okay, maybe that I can get it later. But now it's almost not the next one, is the next but one. And if I get the connection, I will show you the position of this file in my website. Let me see. And here it is. Basically, what I'm talking about is what is called here model calibration. First of all, let me clarify the terminology, because there are more than one term. There is more than one term that can be used to mean parameter estimation. So basically, we can speak of model estimation, and then let me say that we can say here model for parameters. So you can say model estimation, or you can say parameter estimation. Usually we use the singular even if you have more than one parameter. So basically you can say model estimation or parameter estimation. They are synonyms, but also for estimation there are several synonyms. And I can mention calibration. I can mention optimization. So basically you can say model calibration, model optimization, model estimation, or you can say parameter estimation or parameter calibration or parameter optimization. They are synonyms. I want to be clear because the literature is using several different terms. Also there is another one which is model parameterization, which is again a synonym. Of course, you could not say parameterization, but you can say model parameterization instead of model calibration. I would say that the most used in hydrology is model calibration or parameter calibration. This is probably the most used. So basically, in practice, we have to find a value for one or more parameters, the proper value. And as I said, it's important to get a preliminary guess. The preliminary guess usually is also obtained by several application of models. And by the way, I forgot to tell you that a good guess of the K value for the linear reservoir is the time of concentration of the basin. There is also a mathematical proof of this, but we forget it because it's a bit too complicated. So I forgot to tell you when I spoke about guessing the K value for a catchment. A good guess is the time of concentration, which is not a really helpful suggestion because I told you that the time of concentration is very difficult to estimate, but at least you have an order of magnitude. So the pour river, I told you that the time of concentration is about 1 week, so now you know that an optimal value, a good value, a good guess for K for the pour river could be 1 week. So it's important to get this preliminary guess. But then let's see how we can finalize this parameter calibration. Let's forget for now what is model validation. We will see later, okay? But basically what I can anticipate is that validation is the process of verifying the parameter values that were obtained through calibration. So through calibration you obtain the parameter values, and through validation you check them. this is just, it's just repeated what a parameter is. We already know this. And basically here you see a motivation for doing this. Why an hydrological model has parameters? Because an hydrological model is uncertain. So for the fact that it's uncertain, you need to adapt it to the specific case study, to the specific problem. And therefore you need a formulation for the model that is flexible. We couldn't use a rigid formulation, we need a flexible one. So this is why we introduce parameters in an hydrological model. In principle, in physically based models, we could avoid the use of parameters if we were able to write a perfect mathematical representation of the rainfall and off transformation. This perfect representation wouldn't include any parameter, because it would be just the application of physical principles, and therefore you don't see parameters in fully correct physical laws. If you think Newton's law F equal ma, you don't have any parameter here. F is the force, m is the mass of the body, a is acceleration. You don't need to introduce here a kind of alpha or k to adjust it. It's correct. This is a correct relationship, and you don't need any flexibility. So in principle, this should be possible also for hydrological models, but actually, I already mentioned to you several times that hydrological models are affected by uncertainty. The uncertainty is related to the fact that rainfall estimation is uncertain by itself, and the description of the involved physical processes is uncertain, and therefore you need to introduce parameters. So in the linear reservoir, we assume that the discharge is proportional to the storage. But if we were able to apply a conservation of energy relationship, we would avoid any parameter there. Okay, so basically we have these parameters which allows us to fit the model to our process, to improve the fit of the model of our process. So basically, let's identify two main categories, two main groups of methods that can be used to perform model calibration. And these are manual calibration on one end, so manual calibration and on the other end, automatic calibration. So what is manual calibration? First of all, let me make a premise. In order to perform calibration, you need data. So let's take this statement as an axiom. You need data. In a wider sense, we could say you need information. But because data are a piece of information, and in a more practical way, I prefer to say we need data. So basically, you need, what is the purpose of your model? The purpose of your model is to transform rainfall into river flow. And therefore, to calibrate the model, you need rainfall and river flow data. So basically, you need to check your model by running it in a known scenario and to compare the model response with the observed reality. I repeat. Basically, in order to perform calibration, you need to run your model to reproduce a known scenario so you can compare your model simulation with the observed reality. This is how calibration is carried out. So basically what we could do is, for instance, take an observed PT. So basically take a yetograph, and the yetograph is something like this. Take this observed yetograph, and then take an observed hydrograph. So take an observed QT, which would be something like this, for instance. This is reasonable. You have a first peak due to rainfall, and then you have a slight decrease because you have no rainfall for a while, and then a second rainfall, and then a second peak which is higher because it rains over the back catchment. So basically this is observed. These are observed. And then at this stage, you run your linear reservoir or whatever model and try for a given k value, so you assign k and you assign it by guessing, and then you plot your hydrograph and then the resulting hydrograph, and then it could be something like this. So basically you try with a k value, and then you run the linear reservoir, and then you get a yetograph, an hydrograph, a simulated hydrograph. And then you judge, based on your expertise, if you are happy with this simulation. If you are not happy, then you change k, change k, and then you may obtain another yetograph, like for instance this one. So you change k and you get another one. And then, by trial and error, you finally get to a k value that makes you happy. This is manual calibration. Again, manual calibration is driven by visual inspection. So you guess a value of k, and you visualize the resulting hydrograph. If you are not happy, you change k, and then you visualize another hydrograph, and you repeat this experience until you converge to an hydrograph that makes you happy. And then you retain this k value. This is a trial and error procedure. This is quite easy to make. If you have just one parameter, as for the case of the linear reservoir, is easy. Because you will see, once that you have the algorithm written in R, to run the linear reservoir model takes less than 1 second. So it's very easy to change the K value and to run another trial. So basically each trial takes maybe 5 seconds, and then it's very easy, if you have just one parameter, to explore what are the possible results and to identify the best one. The problem becomes more complicated once that you have more parameters, because think of the situation in which you have 2 parameters. Then if you have just one, sorry, I go back one step. If you have just one parameter, you have only 2 choices. One that you guessed a value and you see a result. Either you decrease it or you increase it. And therefore it's very easy to make a trial by decreasing, to make a trial by increasing, and then to move forward. It's very easy. If you have 2 parameters, you have 4 choices. Increasing one, increasing the other one, or increasing one, decreasing the other one, or the opposite, you understand, 4 choices. So to explore all the possible combinations becomes much more time consuming. And if you have 5 parameters or 10 parameters, think at the many possible combinations that you have to explore. It's almost impossible by trial and error. And also it's difficult for you to keep memory of the results, because if you have just one parameter, it's easy for you to memorize what happens if you decrease or increase the parameters. If you have only 2 parameters, still, it's already much more difficult for you to memorize what happens for different combination of the parameters. So the moral of the story is that if you have a simple model like the linear reservoir, you can use the trial and error procedure. It's recommended. If you have already a model with 2, 3 parameters, the trial and error is no more practical, because you run the risk of not converging to the best solution. So at this stage, hydrologists in the 90s, when computing power became available, they started doing research on automatic calibration. Automatic calibration means that the computer makes the trial and error for you. And for the computer, it's easy to keep memory, because once that you have RAM memory in your PC, you can keep memory of all the results. Automatic calibration then. But there is a but. The computer cannot make the visual inspection. The visual inspection is possible for you because it's your experience. The computer doesn't have any experience. It only has the capability to evaluate mathematical relationship and to judge whether a number is greater or lower than another one. And this is the only thing that he can do. And therefore, of course, we need to identify a way in order to check the goodness of the fit of an hydrograph without looking at it. So we have to find a measure of model performance, because computers can compare measures, but they can't compare figures. So basically I have to substitute this visual comparison with a measure. Now let me make another graph here, bigger one. So basically, I have 2 hydrographs. One is observed, and one is simulated between time 0 and time t. So this one is the observed, and the other one with dashed line is the simulated. Typically, these hydrographs, observed and simulated, they have the same area. The area below the hydrograph is the same. Why is that? Because I told you that the area below the hydrograph is the volume of discharge. And given that these models are based on the mass balance equation, usually they preserve the area below the hydrograph, which is the volume of discharge. So the shape of the hydrograph may be different, but the area below the hydrograph Usually it's the same. Unless you increase evaporation, you increase water losses. So the visual comparison tells me very quickly that the simulated hydrograph is in delay with respect to the observed one. But this is not possible to quantify by the PC. We have to identify a measure. So now the question is, what measure can I define to evaluate the goodness of the fit provided by this simulated dashed line hydrograph? So this is observed and this is simulated. These measures of the goodness of the fit are called, I write here, objective function. And we can easily gain an intuition that the goodness of the fit is is summarized by the simulation error, which we can define at each time step. So at each time step, we can define a quantity. Let's call it epsilon t, which is Q observed at time t minus Q simulated at time t. It doesn't matter if you subtract the simulated from the observer or vice versa. Let's call it the difference. The error is the difference between the observed and simulated variable. And of course this can be defined at each time step. So it's quite obvious for us to guess that this objective function, which is a measure of model performance, can be expressed depending on this error, simulation error. And it's quite obvious that if the error was identically zero, the match is perfect, the simulation is perfect. So in the same way, we can guess that our measure of model performances should deliver a good response if the error is zero, and a bad response if the error is increasing. So how can we define then the subjective function depending on the error? There is one objective function that is largely used, and I'm sure that you already used it in some application, maybe implicitly. And this objective function is called the least square objective function. Least squares, which is on the top here. And here, basically, here I used x instead of q to indicate the variable that is simulated, because this is a general treatment, so I prefer to use the general symbol. Usually I use q for the river discharge and x for the generic variable. And I use a hat x to mean the simulated one, and the x without any other addition, other specification to indicate the observed. And basically, the least squares objective function, which is called here f theta, is given by the sum of the squared epsilon the sum of the squared errors and I need to give some specifications here, but first let's understand that it's very simple. I have the simulation error, I square it, I take the summation of all the squared errors, and then I get my objective function. And you can easily understand that if the simulation is perfect, the sum of the squared errors is 0. If the simulation is wrong, then you get an increasing value of the sum of the squared errors. How many terms does this summation count? Let's say that it is extended over I varying from 1 to capital N. Capital N is the number of observed discharges that I have available. And so let's put an I here. Sorry, I here. I here. So let's suppose that we have 100 observed river discharges, and then we extend the summation from I equal to 1 to N. I is an index that stands for time, basically, because river discharges are a function of time, are expressed as a function of time, and therefore we can extend the summation to all the time steps. And then you may wonder what is theta. Theta is the vector of the parameters to be estimated. The objective function depends on the parameter values. Once that you guess a parameter, once that the PC guesses a parameter, then for varying parameter you get a varying objective function. You may have a parameter combination, a parameter vector that gives to you the perfect simulation, and then the objective function is 0. If you change the parameter vector, you get different values of the objective function. And this is what we want, because we want a measure of the goodness of the parameters. So, of course, the objective function should depend on the parameters. And with theta, I am indicated here the parameter vector. Why a vector? Because the parameter may be 1, but may be more than 1. I told you that there are models with 10 parameters, and therefore I need to put a vector here. So basically, what should we do? What should the computer do? Should try several different parameter combinations by picking them by chance, and then keep memory of all the values of the resulting objective function. It computes 1 million of trials, and then keeps the best value of the objective function, goes back to it, and looks at the theta that gave the best value, and gives back this response. And the response is the best parameter vector theta is this one, because it was the one that after 1 million of trials resulted in the lowest least squares. Result in the least squares. Okay, least is already means small, the smaller. So basically, this is what the PC does. We tell it that we have like 5 parameters. We tell it what the parameters are, and then he picks the parameters values by chance. And of course, there are also some algorithms that try to benefit during this search from the previous results in order to drive their search. So the first algorithms, indeed, they took the parameter combinations by chance. But then people realized that, you know, if you look by chance, you may miss good solutions. So they realized that an efficient search was needed, and so the analysts developed several algorithms, and in R there are many of them, to perform a driven search. of the best parameter combination. It's not our job to learn more about how these algorithms work. We just want to know which one works best for our purpose, and Emanuele on Thursday will suggest you one, and then we just apply it and retain the results as long as we are happy, because at the end of the story, what you need to do is, in any case, to look at the final results, to look at the goodness of the fit, to make this visual comparison, but you make it just once. And if you are not happy with it, you may perform another search. Okay, this is what basically you will do on Thursday. And this is just one example of objective function. And let me say that this is called a quadratic objective function. And what's the reason why it's quadratic? What's the reason why people thought to take the square, the power of 2, the squared error? The reason is that, of course, you want to avoid compensation between positive and negative errors. Because if you don't square the error, you may end up with a solution where positive errors compensate negative errors. This is something that you don't want. Like in this case, you see that you have positive errors here and negative errors here. So if you didn't square the errors, you may end up with an error that is 0, even if the hydrograph is clearly wrong. So you don't want to use the error with sign. So this is one reason why people decided to take the squares. And another reason is purely statistical. There is a statistical proof that proves that if you use this objective function, you get good results. Let me use a loose terminology.